All right, so my name is Guannan, and I'm going to talk about hallucination-resilient LLM-driven sound and tunable static analysis. And this is joint work with Zhang and Caterina. So what is static analysis? Right. The basic job of static analysis is to predict the behavior of a program without actually running it. And now suppose the problem. Now suppose we have a program, and here are some concrete traces of the execution of this program. And the job of static analysis is to come up with an over-approximation that covers all of those concrete execution. Should I continue, or you can fix it? Or is that because the connector? Is better? Okay. So we have this over-approximation about all of those program behavior. And this is an important notion of soundness. So we don't really miss any true behavior of the program. And this is useful, for example, for verification, because once we have this over-approximation, and if it doesn't reach an error, then we can safely conclude that there's no problem, there's no error in the program. And if there's indeed some error and it's covered by this over-approximation, we can say we find a bug in this program, right? So it's useful for bug detecting as well. But also, it's not always possible we can have a perfect over-approximation. Sometimes we just end up with a very coarse-grained over-approximation, and that covers some possible error. We report it in the static analysis, but they're not really something going to happen in the actual execution. So this is known as false positives or false alarms, right? So the goal of static analysis is twofold. One is we want soundness. We want to cover or detect all true errors. We also want to have precision, which means we want to reduce the number of false errors as much as possible. Now, you want to use LLMs to do this kind of static analysis. The problem is how to do that. A popular way is to just really doing prompting of the language model, right? Here we have a Java program, and it's just doing some numeric operations here. And we can have a prompt. The prompt is asking the language model to mimic the execution and detect the division by zero errors. And the language model indeed does a good job. It generates traces describing the execution and report some errors, okay? That seems all good, but the problem is, can we really trust those LLM reported static analysis results? And unfortunately, because of those language models, they can hallucinate. We may end up with the result from the analysis. It misses a true error, which means there are real bugs missed by the language model, but also introduce false positives. So this is really bad. And you may thought we can validate the result from the language model, right? We can use even another language model to judge or validate the analysis result from the first language model. That seems possible, but to really doing this correctly, this becomes another static analysis problem, because without really knowing what's all the true behaviors, the other language model really cannot do anything to faithfully or correctly validate the result. Okay, so this is a problem we want to solve here. And our idea is to use language models as a meta-analysis. So instead of using language models to analyze a program and produce the behavior of the concrete execution, we use language model to analyze the static analyzer and also analyze the current ongoing static analysis. And the hypothesis here is, if language model can truly understand programs, and the static analyzer itself is also a program, so the language model can also understand the static analysis as well, right? So here's a general recipe here. The first step is to identify those precision critical decisions in the static analysis. And those decisions they should not hinder soundness, but also they have a huge impact on the precision. And the second step is during the analysis, we use language model as that decision maker. And when we're prompting the language model, we should describe the process and the implementation of the static analysis. And the prompt should also contain the current abstract state, which contains, for example, the abstract environment, abstract heap, and also those other meta information of the analysis. And finally, the prompt should also instruct the language model to decide for better precision. Okay. This is a general recipe, and with this architecture, we can preserve soundness by construction because those decisions, they have their own decision space, and neither or any decision is indeed sound. And if we're lucky enough, we have effective prompting, then we can improve the precision under this architecture, right? So in this precision paper, we did a case study about the control flow analysis, especially for high order programs. And this analysis task is to determine the functions to be called at each call site. And in general, this is an undecidable problem once the data and control flow are entangled. For example, when you have first-class functions in Scheme or other function languages, or even when you have dynamic dispatch in Java, or when you have indirect call with pointers in C. So you face the same problem of this undecidable control flow analysis. And our specific analysis we're working with is this abstracting abstract machine framework, which is a paper published many years ago at ICFP 2010. And in this framework, analysis is defined as an abstraction of a concrete abstract machine, for example, a CEK machine. And here I show the definition of the abstract state, which contains the expression, environment, the abstract heap, and also the continuation. And the result of this analysis is an over-approximated transition graph of abstract states. So following our recipe, the first step is to identify precision critical tasks in the static analysis. And in this AAM framework, there are several decisions, especially for abstract address allocation, exactly falls into this category. So in our case, we use LLMs as this abstract address allocators. And here there are alloc_v function and alloc_k function. They are used to producing the abstract address for binding values and also for continuations. And those allocation functions, they satisfy those two important criteria. First, they are soundness safe, meaning that any allocation strategy from a finite set is guaranteed to be sound. And there's indeed a theorem showing that. And second, those decisions, they are precision critical, meaning that those addresses produced from those functions, they decide the degree of over-approximation. For example, context sensitivity can be captured under this framework. And the second step is during the analysis, we use the language model as a decision maker. And here on the right, I basically showed ARM prompting. I'm not expecting you can see the details here, but I'm showing highlight some of this here. At the beginning, we describe the data structure used in the analyzer. Like here, we describe the structure of the abstract state, okay? Which have those different kind of states definition containing the program expression, the environment, the binding store, continuation store, as well as the current continuation. And we also describe the protocol of to interact with the language model. Like here, we specify the JSON format when we're querying a decision from the language model. And also, correspondingly, we specify the output format as well as in JSON format. And so the language model should produce exactly this JSON format. And then our analyzer will parse this result and put those things back into our analyzer used as the abstract address. And we also need to explain the logic behind the allocation and ask the language model to reason with abstract states. And this is basically to say we need to improve precisions in those prompts. So we have implemented this idea in a prototype analyzer. We use Scala to implement those analyzer, and we call language models. There's a LangChain4j framework to invoke the language model. We do have the open source here. We have done some very preliminary evaluation on micro benchmarks using GPT-4o. And here I show the result of the evaluation. There are only several micro benchmarks, and we also compare with existing deterministic allocation strategies showing in the top of the table. And because of language models, they are non-deterministic, so we run 3 times of our own analyzer and report those numbers. And here, for those 4 benchmarks, we show the number of nodes or abstract states and also the number of edges, and use that as an approximation about precision. And you can see here, 3 of those benchmarks, we achieve the best precision compared to those deterministic existing strategy. And one of them on this MJ09, we have a pretty decent result. It's pretty close to the best one that is highlighted in the red box here. But overall, the result is encouraging, and we haven't really, we're still working on extending this thing to a larger benchmark. So to conclude, our position is to use language model to analyze the analysis, and we have a recipe for sound, precise, and tunable static analysis driven by language models. And the first step is to identify those precision critical decisions in static analysis, and the second step is to using language model for that. And in the paper, we also discuss other future opportunities, because other than the control flow analysis we have done in the paper, there are other kinds of analysis you can also discover this opportunity to apply. For example, for numeric analysis or termination analysis. And for the second recipe, the second step in our recipe is really about how we can use language models better. And there are also opportunities to do that. We can try different prompt optimizations, fine-tuning, or even reinforcement learning of the language model for better precision. This is the end of my talk. Thank you. From what we observed, it's pretty consistent. We try 3 times for each of the benchmarks. Be consistent, but there are definitely some randomness there. Yeah.
So I noticed you measured the precision, but you didn't say anything about the performance of the approach, because the allocation function is called quite a lot in these kind of analysis. What's the results there?
So currently our prototype calls LLMs every time when we need to allocate an address. This is indeed very costly. So some optimization, maybe we just do this selectively, or we can just customize the prompt, or just selectively choose some of the prompt instead of giving all the, or reifying all those abstract states. But that's kind of like optimization there.